Remember I said that I was looking for something that made more sense than just environmental effects on our aging. There had to be some kind of clock. Well, here it is. When I heard somebody describe this in 1992, I was in an audience just like this. I was instantly up at the front to talk to this guy, and I was working for the guy 2 weeks later to try to figure out a way to prevent this. So the best example that I can give you that telomeres affect aging is that there are people on this planet that are born with telomeres already short. And these kids suffer from every age-related ailment that normal old people do. They get, osteoporosis, they get clogging of the arteries, they get Alzheimer's, they get everything. They die of old age at 20 years old. And if we could find a way to prevent telomere shortening, or even reverse telomere shortening, this would be a cure for this disease. Because even though these kids have another mutation called lamin A that causes the telomere shortening, their only problem is they have short telomeres. If we could lengthen them, they'd be living totally normal lives. And believe me, that's something that scientists at my company would really like to do, even though there's only 250 kids at any one time on this planet that have this disease. Now, they're not the only ones. We all suffer from short telomere diseases. In fact, now every single disease you've ever heard of has now been published in scientifically peer-reviewed journal articles showing that the length of your telomere affects those diseases. I mean, if anybody sees any particular disease up there that they'd like to talk to me about later, feel free, because I can refer you to papers, publications, everything that's associated with telomeres here. But what I'd like to do is I'd like to focus on the first two on the top, cardiovascular disease and cancer, just for a minute, because they are the number 1 and 2 causes of death in our world. What is done is that there's been now so many papers published on cardiovascular disease and cancer that scientists have now summarized all these papers and published what's called a meta-analysis, which means this is a summary of all the other papers as to what they're all saying. This meta-analysis is saying that short telomeres increases your risk of cardiovascular disease. The same is done for cancer. Even more papers have been published showing that when telomeres get short, you have an increased risk of getting cancer and a decreased risk of fighting your cancer. I'd like to spend a little more time on this one because this one's really important. Think about your chromosomes now as a shoelace again, and when the shoelaces get really short, you start having chromosome breakage. Joining the chromosomes start falling apart. You can see this in the microscope when you take cells from a cancer person. You can see these physical changes in the chromosomes because they're big changes. Now, what happens is these mutations cause the cancers. Okay? Every time somebody gets cancer, it's due to mutations in their chromosomes. But what's causing the mutations? Well, short telomeres is now known to be a major cause of the mutations that lead to cancer. And what's even just as big a problem is when you do something like chemotherapy to try to treat that cancer, you can kill 99.9% of those cancer cells, but because of the high mutation rate, some of those cells, 0.01% of those cells, are going to survive. They're going to mutate to be able to survive whatever you treat them with. And as a result, those are going to grow back. So the bottom line is we got to keep our telomeres long. We got to keep our telomeres long to keep from getting cancer. We got to keep our telomeres long to increase the chances that therapies like chemotherapy will kill our cancer, and we got to keep telomeres long to help keep our immune system to continue to fight the cancer. Because our immune system is our best defense against cancer. So it's not just aging we're talking about today, but cancer is an aging-related disease given the fact that it's more prevalent in the elderly than any other age. The take-home message today is bad things happen when telomeres get short. This is something I go around saying. I want everybody to just think of bad. Short telomeres is bad. Long telomeres, there's nothing wrong with long telomeres. Nobody's ever found anything in the Petri dish or in different tissue samples. Nobody's ever found anybody that was suffering from anything because their telomeres were too long. So we can get our telomeres long. It's really good. The only thing that long telomeres do is make you younger. And as I mentioned before, I'm going to show you some stuff where people have actually demonstrated that in mice. If you want to learn more, because this is really, like when I'm speaking at a medical conference, I will go into a lot of details, show a lot of data. But instead here, what I'd like to do is anybody who wants to learn more about how telomeres affect every kind of disease or thing in your life that you can imagine, go to something called PubMed, P-U-B-M-E-D. It's short for Publications in Medicine. You don't need to write down the website because you can just Google it and find the website. But just type in telomere and then all capitals A-N-D and whatever, like you want to do cancer, multiple sclerosis, macular degeneration, any kind of thing. Just find it, and you'll find all the scientifically peer-reviewed journal articles on that subject. So what I want to say is quit reading the press releases in newspapers, quit listening to doctors who get on talk shows, because they're all supported by special interest groups that want to tell you something that's not really true. And so here's where you can find the truth. Because so if you want to know, is coffee good for you? This is where to find it. Is ibuprofen bad for you? Is aspartame bad for you? Find out the facts here. This is where to do it. But also learn all about everything you can about telomeres. Okay, so I've just spent a lot of time telling you about the problem. We have telomere shortening that's causing us to get sick and old. Every kind of disease you've ever heard of is affected by the length of your telomeres. We want to keep them long. Well, how are we going to do that? Well, one of the first things we got to do is we got to figure out, why do they get shorter? And so what I want to do to describe how they get shorter and why they get shorter is I want to come up with an analogy. And the analogy would be to think of your chromosome, your DNA, as the top row of bricks on a brick wall. Now, if you think about it, every time you have a cell, we're made of 100 trillion cells. Every time one of those cells want to divide to make 2 new daughter cells, everything in that parent cell has to be duplicated, so that when you get the 2 daughter cells, the contents inside those cells are identical to what that parent cell was. So everything has to be duplicated, and that includes that DNA molecule that I told you, that's 100 million bases long. And it's duplicated through a process called DNA replication. So think of the chromosome now as this top row of brick on a brick wall, and when the cell wants to divide, it's going to make a new row of bricks on the brick wall. And one row is going to go into one cell, and one row is going to go into the other cell. So let's get rid of the other bricks and get rid of the cat. And now a cell's getting ready to divide. The bricklayer comes along and starts laying the bricks. Now, this is a long, arduous process. Remember, the chromosome's about 100 million bases in length, and so it takes a while to do. And also, it's got to be done accurately, because any misplaced bricks are going to lead to mutations. Now, the problem that we want to really focus on here is not really what's happening here, but what's happening way over at the telomere, at the very end of the chromosome. Now, we are smart enough to know not to stand on top of the brick wall when we're making a brick wall, or we're making a new row of bricks, and you'll see why. Because when this bricklayer gets to the end, he can't put a brick in the last place that he was standing. Okay, so what's the point of all this? The point is that this new chromosome is shorter than the first chromosome. The reason why the chromosomes get shorter every time a cell divides isn't because something chews them away. It's because our cells lack the ability to be able to duplicate the old chromosome into a new one, lacks the ability to replicate all the way to the very tip. As a result, the new chromosome is shorter. And so the cell divides, and now the cell gets ready for another division. Again, the bricklayer come along, and again the bricklayer is going to fall off the end. But now the chromosome's even going to be shorter and shorter and shorter with every cell division. As I said before, there's absolutely nothing we can do about this. No matter how well we eat or exercise or do everything our doctors tell us to do, we can't stop this shortening. I call this basal level telomere shortening, meaning this is the slowest that we can get our telomeres to shorten. As I mentioned before, there's nothing we can do to stop this, but we can accelerate this. So if anybody wants to live or age faster than they are right now, this is how to do it. And that's anything related to an unhealthy lifestyle. So obesity, lack of exercise, psychological stress, smoking, all these things cause the production of free radicals or inflammation that will actually accelerate the rate. It will cleave the telomeres, make them shorten at a faster rate. So I call this accelerated telomere shortening. Now, there are things we can do to stop this, and that includes like exercise, quit smoking, lose weight, meditation. Also, you can do things like omega-3 fatty acids, vitamin D, antioxidants. And you'll hear about a lot of products on the market today that are saying that they protect your telomeres and stuff. And that's what they're doing. They're providing you with things like vitamin D, omega-3s, and antioxidants that will help reduce the rate of this accelerated telomere shortening. But they don't lengthen your telomeres, and that's what we really got to do. We got to, because it's only going to decrease the accelerated telomere shortening. We're still going to have that basal level telomere shortening. As a result, nothing can stop it. We got to figure out a way to stop it and lengthen it, and that's what I'm working on. The solution. Let's see. There was something I wanted to say. Okay. Yeah, that's what I wanted to say. The solution is that there are cells in our body that already don't age. Okay, we've known this for a long, long time. I was going to give away one of my books with this question, but I thought, shoot, there was a reason I wasn't going to, and it's because I don't have enough books. Okay, so we have aging occurring that doesn't occur in our reproductive cells. And this has been known for a long time because our children are born younger than we are, and they come from our old cells. So something in our reproduction process is preventing our cells from getting, those cells from getting older. That's why our children are born young. Well, what we discovered was that telomeres don't shorten in our reproductive cells either. They're the only cell in our whole body where we don't have telomere shortening. I said before, every time a cell divides, the telomeres get a little shorter. That's true in every single cell of our body except our reproductive cells. So I got into this business by trying to find out why these cells don't have telomere shortening. Because we were understanding that, as I already said, we pretty much understand why they shorten. What do these cells do to keep them from shortening? And as a result, I discovered this enzyme called human telomerase. Screen bars here is showing the double helix. The DNA is a double helix. Telomerase is shown as a factory. The factory is adding bases, these beads on a string, they're adding bases to the very end of the chromosome, making it longer. And so this is how the reproductive cells do it. Think of it like a clock. When a regular cell divides, telomeres get shorter. It's like clock ticks once. Cell divides again, telomeres get shorter, it ticks again. But in our reproductive cells, the cell divides, telomeres still get shorter, but then telomerase pushes it back a tick by re-lengthening the telomere. Divides again, it gets shorter, telomerase pushes it back, so the clock doesn't tick. It's like a tug-of-war. Shorten, lengthen, shorten, lengthen, shorten, lengthen. That's why in our reproductive cells, we don't have any telomere shortening.